medicine, mathematics, metallurgy, engineering, etc. Indian physicist Sir C.V. Raman is one of them. Raman effect was discovered by Sir C.V. Raman on 28th of Feb 1928. National Science Day is celebrated in the honor of Sir C.V. Raman and his great discovery. Shri Vaishnav Vidyapeeth Vishwavidyalaya organizes Sir C.V. Raman Memorial Oration on National Science Day every year since 2019. Before moving further, I request all the dignitaries and audience to join traditional auspicious lamp lighting ceremony and Saraswati Vandana as a tribute to the goddess of wisdom, Ma Saraswati. I request technical team to kindly proceed. Thank you. The presence of our distinguished chief guest, Professor Sujata Ramdorai, adds immeasurable value to this gathering. Ma'am, we are delighted to have you join us for this momentous occasion. Dear ma'am, on behalf of Honorable Chancellor Shri Purushottam Dasji Pasari and Vice Chancellor Shri Vaishnav Vidyapeeth Vishwavidyalaya, Dr. Upinder Dhar, our bouquet is being presented to you through virtual gestures.
Thank you. Thank you.
Thank you, ma'am. We hope you accept the same warmth and appreciation as if it were presented physically to you.
Sure.
Bharat Ratna Sir Chandrasekhar Venkat Raman, a great Indian physicist and Nobel laureate whose entire life is a journey of exploration and discovery, a journey that celebrates the relentless pursuit of knowledge and the boundless curiosity that drives us forward. Let us all have a quick tour to the glimpses of his life through a short documentary.
Most prominent Indian scientist in history, C.V. Raman was the first Indian person to win the Nobel Prize in Science for his illustrious 1930 discovery, now commonly known as Raman effect. It is immensely surprising that Raman used equipment worth merely rupees 200 to make this discovery. The Raman effect is now examined with the help of equipment worth almost millions of rupees. Chandrasekhar Venkat Raman was born at Tiruchirappalli in Tamil Nadu on 7th November 1888 to a physical teacher. Raman was a very sharp student. After doing his matriculation at 12, he was supposed to go abroad for higher studies. But after medical examination, a British surgeon suggested against it. Raman instead attended Presidency College, Madras. After completing his graduation in 1904 and MSc in Physics in 1907, Raman put through various significant researchers in the field of physics. He studied the diffraction of light, and his thesis on the subject was published in 1906. Raman was made a Deputy Accountant General in Calcutta in 1907 after a successful civil service competition examination. Very much occupied due to his job, he spent his spare time in the evenings conducting scientific research at the laboratory of the Indian Association for Cultivation of Sciences. On certain occasions, he even spent entire nights there. Such was his passion that in 1970, he resigned from the position to become the Professor of Physics at Calcutta University. On a sea voyage to Europe in 1921, Raman curiously noticed the blue color of the glaciers and the Mediterranean. He was passionate to discover the reason for the blue color. Once Raman returned to India, he performed many experiments regarding the scattering of light from water and transparent blocks of ice. According to the results, he established the scientific explanation for the blue color of seawater and sky. There is a captivating event that served as the inspiration for the discovery of the Raman effect. Raman was busy doing some work on a December evening in 1927 when his student K.S. Krishnan, who later became the director of the National Physical Laboratory, New Delhi, gave him the news that Professor Campton had won the Nobel Prize on scattering of X-rays. This led Raman to have some thoughts. He commented that if the Compton effect is applicable for X-rays, it must also be true for light. He carried out some experiments to establish his opinion. Raman employed monochromatic light for the mercury arc, which penetrated transparent materials and was allowed to fall on a spectrograph to record its spectrum. During this, Raman detected some new lines in the spectrum, which were later called Raman lines. After a few months, Raman put forward his discovery of Raman effect in a meeting of scientists at Bangalore on March 16, 1928, for which he won the Nobel Prize in Physics in 1930. The Raman effect is considered very significant in analyzing the molecular structure of chemical compounds. After a decade of its discovery, the structure of about 2,000 compounds had been studied. Thanks to the invention of the laser, the Raman effect has proved to be a very useful tool for scientists. Some of Raman's other interests were the physiology of human vision, the optics of colloids, and the electrical and magnetic anisotropy. Sir C.V. Raman became the Fellow of the Royal Society of London in 1924. A year later, he set up Raman Research Institute near Bangalore, where he continued scientific research until his death, which was caused by a strong heart attack on 21 November 1970. His sincere advice to aspiring scientists was that Scientific research needed independent thinking and hard work, not equipment. Thank you for watching.
Thank you, technical team, for playing this documentary. On behalf of Honorable Chancellor Shri Purushottam Das Ji Pasari and Vice Chancellor Shri Vaishnav Vidyapit Vishwavidyalaya, Dr. Upinder Dhar, and our chief guest Padma Shri Professor Sujata Ramdurai, a tribute to Sir Chandrasekhar Venkat Raman is paid virtually. Thank you, technical team. Now, I request Honorable Vice Chancellor Shri Vaishnav Vidyapit Vishwavidyalaya, Dr. Upinder Dhar, to welcome our guest with his warm words and gesture. Over to you, sir.
Good afternoon to all of you. At the outset, I would like to extend a very warm and hearty welcome to Professor Sujata Ramdurai on this very special occasion. Like we have been doing in the past, we celebrate Science Day on 28th of February. In fact, it is officially called National Science Day, which commemorates the discovery of the Raman effect by Dr. C.V. Raman, for which he won the Nobel Prize in Physics. Every year on this particular day, that is 28th of February, the government of India felicitates scientists from various fields for research and for their contributions. National Science Day's main objective is to increase awareness among people about the importance of science and technology in their lives. Dr. C.V. Raman officially declared on 28th February 1928, as we have seen in this short film just now, that he had invented the Raman effect. He was then awarded the Nobel Prize in Physics in 1930 for his findings. Expected it in 1929, but it was not awarded to him in 1929. But the next year, that is 1930, this award was conferred on him. When at that time he was president of the Indian Science Congress Association as well. He was then awarded, as I said, this Nobel Prize. The National Council for Science and Technology Communication, that is NCSTC, put forward a proposal for the National Science Day to be celebrated on 28th February every year to pay tribute to this achievement. Following this, the government of India accepted the proposal, and the first ever National Science Day was celebrated on 28th of February 1987. National Science Day's primary objective is to ignite an interest in science, inspire people, particularly young people, especially students, to perform new experiments and make them aware of the latest developments in science and technology. Several scientific activities and programs are organized on this day. So far as our university is concerned, besides routine activities, quizzes, we have made it a point that we invite a well-known and eminent scientist on this day so that we can know more about the concerned scientist, the scientists' concerned scientists' contributions to science and technology, and we would say to the humanity. All of us know why science is important. Science has contributes very significantly to the quality of life. The quality of life that we are enjoying today is the outcome of the contributions made by the scientists. Therefore, these contributions made by great scientists cannot be ignored. See, interestingly, 28th February was the day when Raman effect was announced. It is neither the birthday of C.V. Raman nor the anniversary. So that is very interesting that this is one of those important days when science is actually celebrated. Raman effect, it is the day when Raman effect was announced. It is not the day when C.V. Raman was born. C.V. Raman was born on 7th of November, 1888. So 7th November was not declared as Science Day, but it is 28th February. That is very interesting to note, which is not so in other cases. So we are very happy to pay tributes to this great scientist and great son of the soil. And we are eagerly waiting for the deliberation by Dr. Sujata Ramadurai, therefore not speaking much because teachers have a tendency to go on and on. So I cut it here. And once again, I welcome the eminent speaker for today's webinar. Thank you very much.
Thank you very much, sir. Now I request Dr. Neetu Kataria, member of Science Club, to read the citation of our esteemed chief guest. Over to you, ma'am.
Thank you, ma'am. Good afternoon to all. It is a matter of pride privilege for me to read the citation for Padma Shri Professor Sujata Ramdorai. I quote, Professor Sujata Ramdorai is an algebraic number theorist known for her work on Iwasawa theory, the study of objects of arithmetic interest over infinite towers of number fields. Presently, she is a professor of mathematics at University of British Columbia, Canada. She carried out her doctoral research work at Tata Institute of Fundamental Research, Mumbai, and served at various institutions, including Ohio State University, Indian Academy of Sciences, Chennai Mathematical Institute, and Tata Institute of Fundamental Research. Professor Ramdorai authored 2 books, more than 50 research papers in peer-reviewed journals, and supervised 5 PhD students and many master students. She is also on editorial board of various research journals and conference proceedings. Professor Ramdorai is member of the scientific committee of several international research agencies, such as the Indo-French Center for Promotion of Advanced Research, Banff International Research Station, International Center for Pure and Applied Mathematics, National Knowledge Commission, and Prime Minister's Scientific Advisory Council, Government of India. Professor Ramdorai has been honored as Alexander von Humboldt Fellow, and presently she is Canada Research Chair in University of British Columbia. Professor Ramdorai, one of the finest Indian mathematicians, received the Krieger-Nelson Prize in 2020 by the Canadian Mathematical Society. She is the first and only Indian to win the prestigious ICTP Ramanujan Prize in year 2006 for her contribution in the field of complex geometry, topology, number theory, and cryptography. She is a recipient of the Shanti Swarup Bhatnagar Award in year 2004. Professor Ramdorai has contributed significantly to establish Ramanujan Math Park, an Indian museum and activity center dedicated to mathematics education located in Chittoor, Andhra Pradesh. She was conferred Padma Shri, the 4th highest civilian honor by the President of India for her distinguished work in the field of science and engineering in year 2023. Unquote. Shri Vaishnav Vidyapit Vishwavidyalaya is privileged to present this citation to Professor Sujata Ramdorai for gracing the 6th Sir C.V. Raman Memorial Oration as chief guest on February 28, 2024.
Thank you, ma'am. Now I request our esteemed chief guest to kindly accept the citation virtually.
नहीं ये तो उसके एडवर्टीजमेंट जो आएगा पीएचडी का अखबार वगैरह
Thank you. I have one correction here. I'm not the only Indian. I was the first Indian, but subsequently and happily, there are 3 other Indians who have won the ICTP Ramanujan Prize. So I would like to mention it.
Okay, ma'am, we will note this correction, ma'am. Thank you, ma'am. Now we have reached the point for which all of us are eagerly waiting to hear the lady who is an epitome of unwavering dedication and innovative thinking, a great mathematician whose brilliance is only matched by her simplicity. I request Professor Sujata Ramdorai to grace us with her profound thoughts and deliver 6th Sir C.V. Raman Memorial Oration. Before I hand over the session to our esteemed resource person, I request the audience to please put their questions in the chat box for question and answer session after the oration. Over to you, ma'am.
Thank you. Thank you for the invitation and for the kind words. I hope I can share my screen.
Yes, ma'am.
Okay, let me find where it is now. Yeah, I think it works. Let me go to the first. Yeah. Can you see the screen? I'll put it in full screen mode.
Yes, ma'am. Screen is visible to us. It's not full screen, ma'am, yet.
Yeah, now is it full screen?
Let us wait for a moment, ma'am.
Is it full screen now? No.
Ma'am, it is perhaps because of PDF, it's not covering the entire surface.
Screen. I don't know what to do about this. Let me try again. I'll stop and then let me try again.
Okay, ma'am. Yeah, ma'am. Now it is running on full screen.
Okay, yeah.
Yeah.
Okay. Okay, so I want to talk about prime numbers, and I hope to convince you by the end of my talk about the way mathematics is done and the continuity of mathematics. It has the longest shelf life among various subjects. So let's start with the definition of prime numbers. Prime numbers are those which cannot be factored further, which cannot be broken down further as a product of 2 smaller numbers. So for instance, 2 is the smallest prime number, then comes 3, 5, 7, 11, and so on. And the first recorded history of somebody thinking about prime numbers and setting them down goes back to Euclid, 3rd century BC. That's the first recorded written version. But we know that many civilizations, including India, and of course the Babylonian, Chinese, many other civilizations dealt with prime numbers and thought about prime numbers prior to Euclid, but Euclid's is the first written history that we have, written recorded statement that we have. And then we all learn what today we call the fundamental theorem of arithmetic, which we know as the following statement: any integer, that is any whole number, either positive or negative, any integer, z is going to denote the integers. So any number n can be uniquely factored as a product of prime numbers. So for instance, when you look at 12, you write it as 2 squared into 3. So 2 is a prime number, 3 is a prime number, and so on. 18 is 3 times 6, which can further be written as 3 squared into 2. So 2 into 3 squared. And if you take minus 24, then you break that down as 2 cubed into 3, minus 2 cubed into 3, so on. Now, all these prime numbers, therefore, when we think of them, we can also think of them as irreducible numbers, in the sense you cannot break them down further into smaller numbers. So for instance, 5, the only way you can factor it is 1 times 5. You cannot write it as a product of two smaller whole numbers. So now there's this natural question. Suppose we are given a natural number n, by which I mean a positive integer greater than or equal to 1. What are its prime factors? How do I break it down into a product of prime numbers? We know that by Euclid's theorem, we know that it is possible. But how do we do that? Now, today we can decide whether something divides another number, because even your mobile phone is very powerful and you can multiply huge numbers, you can divide numbers, you can use it as a calculator and so on. But another thing I want to underline in this talk is the power of abstract mathematics, that is the power of human thought. And there were lots of results about prime numbers which were discovered long before the advent of computers. So to keep things in perspective, I'll also indicate a timeline. And the idea is, okay, computers have grown in leaps and bounds. Computers have become so powerful. We all hold a very powerful computer, unthinkable 40 years back in our mobile phone and so on. But many of those things would not have been possible had we not independently proceeded with mathematical research in abstraction, and like Raman said, without heavy equipment, just using the human mind. Today, we can factor numbers that are 8 times larger than what could be done 30 years. Now, I'm sure it's much more than 8 times. I'm sure it's probably 12 times larger with today's computer and today's mobile phone, even. Than 30 years ago, you can factor much larger numbers. But at one time, there was this number which is called RSA 129. So for instance, those of you who had a previous old computer, especially the Linux computers, when you switched it on and you would see a string of various details about the computer, you usually saw RSA. RSA 129, RSA stands for Reverse Shamir Adelman. These were 3 people, and they came up with a number. This number will show up in a few slides, RSA 129. And that was used as a basis of cryptography. That is encoding secret, you have secret messages which you want to transmit. And prime numbers play an important role there. We'll come to that later. And the larger the number, the more secure your crypto system is. So this RSA 129 was one such, which was in 1977. And at that time, they bravely predicted that if you take 40 into 10 to the power 15 years, human years, to break this crypto system. So which is not possible in your or mine or few generations. So they considered that to be a very safe crypto system. So that was in 1977. So very quickly, within 20 years, in 1994, these mathematicians, Atkins, Graf, Lenstra, and Leyland, who were pure research mathematicians, they didn't even use a computer. But with just abstract theoretical mathematics, they factored this number. They found a factor for this number. So which meant that any crypto system which uses this as the basis of encryption is not secure anymore. And that was the implication. So many cryptographic systems even today depend on prime number studies. So that's already one use of prime numbers. But like I said, the study of prime numbers, recorded study, goes back at least 3,000 years back. And at that time, nobody ever had the idea that one day there will be computers, one day these prime numbers will be used as a basis of internet banking or cryptography and so on. So that's typically the way mathematics proceeds. Mathematicians discover because they are challenged by certain problems. And then the beauty of the solution, or the beauty when the different patterns fit and you solve the problem, that's something that drives mathematics research, abstract mathematics research even today. So this is RSA 129. And the factorization is as follows. You can find the two factors. So even with the most powerful computer, today I can safely say that they would not have been able to find the factor if the mathematicians hadn't come up with the theoretical tools necessary. So algorithms available in the 1970s along with today's technology means we can factor numbers. It's more than 40. It's probably 40 digits in the 1970s. Whereas today's algorithms, and by algorithms, I mean pure mathematics implemented as algorithms. And technology, you can factor numbers even on your mobile phone with 155 digits, provided you're a mathematician and you know how to implement that algorithm. Now, here's another famous theorem attributed to Euclid, which says there are infinitely many prime numbers. So we know that the smallest prime number is 2. 2 is the only even prime. All other prime numbers are odd by definition, because if it was an even number, you could break it into smaller numbers and therefore it's not a prime number. And here is a proof which is so elegant. Suppose there are only finitely many primes, and let's call P to be the largest prime. So you have 2, 3, 5, so on up to P. Now, multiply all these prime numbers and add 1 to it. Then let's call that n. Now, we note that n cannot be divisible by any of these prime numbers. We have assumed that there are only finitely many prime numbers. Because if any one of these prime numbers divided n, then it would also divide this number. So it would divide the difference of these two numbers. And therefore, the difference of these two numbers being 1, it would divide 1, which is a contradiction. We know that 1 cannot be broken in any other form except 1 equals 1 times 1. So therefore, this is a contradiction. So n is not divisible by any prime. And this again contradicts Euclid's theorem, because we know that any number has to be a product of prime numbers, whereas here is a number which is not divisible by any of the finitely many prime numbers. So therefore, our assumption is wrong, which means that there are infinitely many primes. So therefore, we have these following questions. Suppose I'm given a set of prime numbers. Can I generate more primes from a given set of primes? And then what is the number of prime numbers which are less than or equal to a given number n? So for small numbers, this is something we can compute. So for instance, if you take 10, then all the prime numbers less than or equal to 10 are just 2, 3, 5, 7. And if you go to 20, then you go 2, 3, 5, 7, 11, 13, 17, 19. These are the prime numbers less than 20. Now Gauss, this remarkable mathematician, at the age of 14, guessed an answer. Again, remember, in those days, there were no computers. He just did a theoretical calculation by hand and then came up with the answer for the second question. So for which we need the following definition. Take any real number and define pi of x to be all the prime numbers which are less than. You're counting all the prime numbers. This is the cardinality of the set of prime numbers which are less than or equal to this real number x. And what Gauss considered was what we mathematicians call as the asymptotic behavior of pi of x. That is, as x tends to infinity, as x grows larger and larger, what is the behavior of pi of x? And there's no pattern. It's not it's not something like, okay, number of prime numbers less than 10 is something. So number of prime numbers less than 100 is going to be 10 times that and so on. So there's no obvious pattern. And that's today called the prime number theorem, the asymptotic formula for pi of x. And remember, Gauss guessed it. He did some computations by hand and said this is the way it behaves. And it took quite a few years, few decades before these two gentlemen, Jacques Hadamard and Charles Jean de Vallée-Poussin. He's French, Hadamard is French, and he's Belgian. The two of them gave a proof of Gauss's theorem, and today, what Gauss conjectured, and today it's called the prime number theorem, and which says that the behavior of pi of x is asymptotic. As x grows larger, it behaves like x modulo ln x. This is a natural logarithm with respect to the base e. So it behaves almost like the ln of x. But what does this tell us? In plain terms, what this tells us is you just look at this table. So for 10, we already counted the primes, 2, 3, 5, 7. So there are 4 primes. For 100, the number of primes less than or equal to 100 is 25. For 1000, it's 168. Now these numbers are growing larger. 10 to the power 4, it's 1229. So there's no pattern here. 10 to the power 6, 78, 498. And all this is calculated using this prime number theorem. And what you learn from this is this following moral, that the larger you go on the real number line, the farther you go, then the prime numbers become scarcer. We know that there are infinitely many primes, but they get farther and farther apart. And this is nicely captured by what we call modular arithmetic. So what we are going to do is take any natural number. Now all the integers, that is positive and negative whole numbers, they are infinitely many, right? You go 0, 1, 2, 3, 4, and -1, -2, -3, so on. So there are infinitely many of those numbers. The integers are infinite. So I want to make that smaller. So what we'll do is we'll group them into classes. So all even numbers. So the simplest example will be take all the even numbers and the odd numbers. So all integers can be grouped into these two classes. It's either even or it is odd. So that is Z mod 2Z. So Z mod 2Z has only two numbers, namely 0 bar and 1 bar. 0 bar will be all the even numbers. 1 bar will be all the odd numbers. And how do you think of this? What is a characteristic of an even number? It leaves a remainder of 0 when you divide it by 2. And then any odd number leaves a remainder of 1. So you can group, given any number, you can take the set of integers and you can group them according to the remainders that you get when you divide the integers by that given number. So for instance, take, let's say you take 3. So when you divide any number by 3, the only possible remainders are 0, 1, or 2. So you have divided all the integers in 3 bins, 3 classes, depending on the remainder that they leave. And we are asking this question about how many prime numbers, how can we generate new primes and so on. So here's an interesting statement. Take two numbers, a and n, and suppose they're relatively prime. So that is co-prime, which means that they do not have a common divisor. So for instance, you can take 6 and 7. 7 is a prime number, 6 and 7 don't have a common divisor. Or you can even take, let's say we take 9 and 16. They don't have a common divisor again, right? So that's what is meant by co-prime integers. So if I take a pair A and D such that they are co-prime integers and D is positive, then I look at this arithmetic progression, namely A plus D, A plus 2D, so on. Then this already contains infinitely many prime numbers. So note that this is not the whole set of integers. What we just proved a while ago was that there are infinitely many prime numbers, but this is among all the integers. But this is a much smaller set than the integers. A plus D, A plus 2D, it's still infinite, but it's a smaller set. And even within this set, the smaller set, you can find infinitely many prime numbers. And in fact, they are in arithmetic progression. Such a sequence is called an arithmetic progression. So it says even if you take two numbers with this property that they are co-prime, even that arithmetic progression contains infinitely many primes. Now the second question, this was sort of extended to a very beautiful result by Terence Tao, who's a Fields medalist and who brought in beautiful techniques from other areas of mathematics called harmonic analysis and so on. He proved the following very interesting theorem along with Green Tao in 2004. For any natural number k, you can find primes which have the property they are in arithmetic progression and k, the length. So you have k primes, k number of them, k of them. And this is true for any natural number. So there are k term arithmetic progression. So you see, so there are all these interesting patterns. Not only are there infinitely many prime numbers, and somehow this is counterintuitive to what we earlier said. We said that as the numbers grow larger, the prime numbers are fewer and fewer. But even when they are fewer, they display these remarkable properties. So here are some examples. So here there are 5 numbers, 1, 2, 3, 4, 5. All of these are primes, and this is the common difference. So the difference between any two primes, this jump, this is called the gap between the two primes. So that's 210 here. So here there are 6 prime numbers with a gap of 16. Sorry, with a gap of 30. 6 prime numbers with a gap of 60. 7, 37, 67, 127, 157, and so on. Now, there was this interesting question. We make the following definition, twin primes. So we know that if we have a prime, the consecutive number cannot be a prime because you take 2 and 3. 2 is even, 3 is odd. After that, if I take any prime number, that prime number has to be odd. So the next consecutive number is going to be even. And we know that even numbers are not prime numbers. So therefore, we define this twin primes, which are those of the form P and P plus 2. And of course, you can include even 2 and 3 in this case, but let's leave that aside. So P and P plus 2, where P is greater than or equal to 3. So 3 and 5 are twin primes, 5 and 7 are twin primes, 11 and 13 are twin primes, and so on. Now there is this conjecture that there are infinitely many twin primes. Not only are there infinitely many prime numbers, but there are also infinitely many twin prime numbers. So again, a pattern, right? We know on the one hand that the gaps between prime numbers become large as we go farther and farther, as we consider larger and larger numbers. But still, there are these beautiful patterns. You can still find infinitely many twin primes. And this was in 2007, 2009. You know, these are some of the examples. I'm sure there are better ones known now. Just look at the size of these prime numbers. So this is 655, 164, 68, 355 into, this is times 2 to this power plus or minus 1. So the digits, number of digits is 1,355,000. So there are more. I mean, these are numbers that I wrote down a long time ago. I'm sure if you do a Google search today, it will give you the largest known twin primes. Now, the sum of the reciprocals of all primes belonging to some pair of twin primes. Let's call that P2. So this is, take all the primes such that P and P plus 2 is a prime. So P comma P plus 2 are twin primes. And then you sum them up. So this is, take the reciprocal 1 over P and then take the reciprocal of P plus 2. So it is 1 over P plus 1 over P plus 2 as you vary over the twin primes. Now, of course, as these are growing smaller, right? Your primes are growing larger. So these denominators are becoming smaller. So this is a convergent sum. So this is a finite number. And this value is called Brun's constant. And it's usually denoted by B prime. So it goes like this. B prime is 1/3 plus 1/5 plus 1/5 plus 1/7 plus so on. Now, here's an interesting story, which again demonstrates the power of abstract thought. There's a mathematician called Nicely. In 2004, he purely theoretical calculations, pure number theory, abstract number theory. He calculated the value of B prime. This is not an exact value. This is approximately this value. That was the constant. And each time people are trying to find better and better approximations to these constants. So Nicely in 2004 came up with this approximation, and he wanted to test it. So he used his computer. At that time, the Pentium chip had just come in and there was this Intel computer, the Intel with the Pentium chip. So he tested it on his computer with the Pentium chip and it didn't match what theory said it should be. So he was slightly worried. He said, okay, maybe my arguments are wrong. Let me go back to the theory. And so he went back, did his theoretical calculations and still got this to be the approximate value. And he tested it on his old computer, which was not using the new Pentium chip. And on that, it gave this value. It said, no, this must be the correct value. So then he wrote to Intel saying, look, there must be some flaw in your new Pentium chip. And Intel said, no, this is impossible, blah, blah, blah. Then he again checked everything, then wrote back to them saying, look, I'm using your old computer and your new computer with the Pentium chip. And there is a difference in these values. So either your old chip was wrong, which I don't believe, because people around the world have been using it for more than 5 years or even 10 years, a dozen years. And if there was a flaw in that, somebody would have spotted it. But this chip is new and this is not agreeing with previous results. So there must be some problem with your new chip. And then Intel took that seriously, investigated and found that there was indeed a flaw in the design of the Pentium chip. And that's today called the floating point flaw. And then Intel recanted, recalled the chips, and then introduced the correct chip. So this again presents the power of abstract thought over technology. Okay, so now let me skip this. What we want to know is, forget this conjecture here. We want to know if I am having a irreducible polynomials, if I'm given k irreducible polynomials with integer coefficients, for what values do I get prime numbers? So for example, and this is a conjecture which is still not proved. There are infinitely many positive integers such that you get prime numbers as values of those polynomials. For example, take this single polynomial, n squared plus 1. Do we know if there are infinitely many primes of the form n squared plus 1? For instance, take 5. 5 is 4 plus 1, which is 2 squared plus 1. And then 17. 17 is 16 plus 1. We know that that's a prime number. 4 squared plus 1, right? So, but then are there infinitely many primes of this form? And what about prime numbers which are sums of 2 squares? So all of these require deeper number theory to answer. We know the answer for many of these questions. And Leonhard Euler is one of the mathematicians who contributed a lot to answering. Of course, he didn't set out to answer these questions, but his work independently in number theory led to answering these questions. Now, here are some other open conjectures. One is Goldbach and Euler. So this is Euler. And Euler conjectured that every integer which is greater than 5 is a sum of 3 prime numbers. Euler showed that if every integer greater than 2 is a sum of 2 primes, then already that is enough to give a proof of conjecture due to Goldbach to imply this. So in other words, if this statement here is true, then this implies that every integer greater than 5 is the sum of 3 primes. So we don't know the answer of this question to this day. Can every integer greater than 2 be written as a sum of 2 primes? If you give any integer, you can write it as a sum of 2 primes. But the larger the integer gets, how do you find the primes? How do you test whether a number is prime? These are natural questions that come up. For most of those, we know an answer today, and these have been implemented in algorithms. Okay. There's overwhelming numerical evidence in favor of Goldbach conjecture, but a full theoretical proof is still missing. Now, there are some special prime numbers. One is called Mersenne primes. These are primes of the form 2 to the power q minus 1. For instance, 7 is a Mersenne prime. 3 is a Mersenne prime. 2 squared minus 1, that is 4 minus 1 is 3. 7 is 2 cubed minus 1. And then there are these Fermat numbers, which are of the form 2 to the power n plus 1. And here's a theorem which says that if I take a number which is of the form 2 to the power q minus 1, and if that is a prime number, then q is a prime number. So this gives us one way of hopefully constructing larger and larger prime numbers. Suppose I know a large enough prime number q. Then I can raise 2 to that prime number and subtract 1 from it. And I'm lucky. If I get lucky, then that number is a prime number. But now this prime number is remarkably larger, much larger than my original number q. So we have to use methods to find out whether mq is a prime. And that is still an open question. Factoring is still open. And as we speak, here are some examples of large numbers, which are prime numbers. So there is something called GIMS, the Great Internet Mersenne Prime Search. So people are using more and more powerful computers to come up with the next large prime number. And why is that? Because when you find a large prime number, you can implement a cryptographic algorithm using that prime number. All that is like a black box. Once you input a larger prime number, the output will be an encryption, which is more secure than the previous one. because the previous one used a smaller prime number. The larger the prime number, the more secure the crypto system is. And let me also define these numbers, perfect numbers. A perfect number is a number such that you take all its factors, proper factors, add them up, then you should get your number. So for instance, the smallest perfect number is 6. Because what are the factors of 6? 1, 2, and 3. 1 times 2 times 3 is 6. And if I add 1 plus 2 plus 3, that's again 6. So such numbers are called perfect numbers. And you know a criterion for an even number to be perfect, again in terms of prime numbers. Now let's move many centuries further compared to Euclid, but not so far behind from our present times. This is Fermat, who was a polymath. And he showed that the first few Fermat numbers, remember Fermat number is here. This is a number which is called a Fermat number. So for instance, if I put n equals 0, I get 2 plus 1, which is 3, which is the smallest number. If I put n equals 1, then I get 2 to the power 2, which is 4 plus 1, which is 5, and so on. So these are the Fermat numbers. And the question was whether Fermat numbers were always prime numbers. He conjectured that all Fermat numbers are prime because the first one, you can calculate them by hand and they turned out to be prime numbers. So F0 is 3, that's a prime number. F1 is 5, that's a prime number. F2 is 17, that's a prime number, and so on. He went up to F4 and, already showing that this is a prime number is hard. You have to know a little bit of mathematics to show that this number is a prime number. And he was rash enough to conjecture that all Fermat numbers are prime. But very soon, Euler disproved that. He showed that this number is not a Fermat number. This is a Fermat number, but it is not a prime number. And it's still unknown. Well, I might be wrong, but till a few years back, the 33rd Fermat number was unknown to be whether it was a prime or not. But now you have some improvements. For instance, you take an odd number which is of this form, a power of 2, and add 1. And if that turns out to be prime, then this m has to be a power of 2. And there's an easy proof. I'm not going to bore you with that proof. It's sort of basic arithmetic. But then you see, this gives us methods to find larger and larger prime numbers. And like I said, why are they interesting? Because using larger and larger prime numbers gives us more secure crypto systems. And the opposite of multiplication is factoring, right? We said if you multiply prime numbers, then you get numbers. That was fundamental theorem of arithmetic. Every number can be written as a product of prime numbers. But if we are given a very large number, we still don't know a method, an efficient method to factor that number. We know that it should be factored. We know that it has prime factors, but it's difficult to find a factor. Let's take a number with, let's say, 10 billion digits. Even the most powerful computer today cannot find a factor within a few seconds. You'll have to run it for a few days and so on. And this lies at the heart of internet security. So you take two primes, multiply them, and then use that for encryption. Again, I'm not going to bore you with this. This is the basics of cryptography. So this, again, what I want to underline from this is the philosophy that people have been studying, mathematicians have been studying about prime numbers for more than 5,000 years. Purely for the sake of studying prime numbers. Why are there infinitely many? How can I find whether a number is prime or not? I know that there are infinitely many prime numbers. How do I find gaps between prime numbers? How do I generate new prime numbers from a given set of prime numbers? These are questions which mathematicians have been independently tackling long before they ever knew that one day there would be computer, one day there would be internet, one day you will have to worry about encryption, decryption, and so on. And today, all that theoretical mathematics is used concretely in encryption, in coding, in cryptography, and so on. Okay, so this is the next point I want to touch briefly upon, which is called primality testing. Meaning, if I give you a number, is there a way that I can devise an algorithm so that I input this number and the output should be yes if that number is prime and no if that number is not a prime. And then we would like an algorithm which doesn't take more and more number of steps as the number grows larger, as the number of digits goes larger. That is, we want to do it in polynomial time and not in exponential time. So suppose that I go from 1 billion digit to 100 billion digits. Then I don't want the computer to take 100 billion years. It shouldn't go exponentially. It should still be possible within a reasonable amount of time. So this means roughly that as n grows larger, the time required to find an answer, you want an yes or no answer. And that time required to find the answer using the algorithm should not gallop, that it should not be growing exponentially. And this is a measure of the complexity of the problem and the algorithm. And the preferred complexity is polynomial time, which means that you'll get an answer within your lifetime or within a week or less time with the more powerful computers. So as a function, the number of steps is a polynomial. That's what it means. Now, this primality testing, it was not even known for a very long time whether one could do primality testing in polynomial time. That is, as a number of digits grows, then the number of steps required to implement the algorithm grows only polynomial and not exponential. This was solved by Agrawal, Kayal, and Saxena, team of Indian scientists. And they proved that primes are in P. That is, you can effectively find whether a given number is prime or not within polynomial complexity. That is not exponential. This uses simple algebra. And the proof is ingenious. And these two, Kayal and Saxena, at that time when they did this, they were actually undergrad students of Manindra Agarwal. And again, excuse me. So again, the proof uses algebra, which was independently developed by mathematicians over the last few centuries. Uses algebra, which is at least 1000 to 1500 years old. So this again goes to prove the point that sometimes abstract mathematics is ahead of its applications. Mathematicians prove results, not ever anticipating that one day it will be used for something. They do it for the sheer challenge or the beauty of the problem. And then to the pleasant surprise or dismay, depending on the way you look at it, it will have these deep applications, which usually take several centuries. For instance, to give an example, the mathematics that's used in mobile phones or in data transmission is just 0.0001% of what is known in that area, in that abstract algebra area, using finite fields and so on. So just 1% of that, or less than 1%, has such fantastic applications. And this was discovered over thousands of years, over hundreds of years. And then suddenly a small fraction of that comes out with such tremendous applications. So that somehow is the nature of mathematics. Okay, I'll close with this one other number system. So I is the imaginary number. I is the square root of -1. So it's not a real number. It's a complex number. So note how things change when you go from Z to Zi. So every integer is also in Zi. Now I know that 2 is a prime number in Z. So in particular, 2 is irreducible. Remember, I mentioned long ago when I introduced prime numbers, we mentioned that primes are also irreducibles, meaning it cannot be broken down into smaller numbers. Whereas here, 2, which is inside Z, and Z is contained in this Zi, but 2 is not irreducible anymore. It's not a prime number here anymore. So 2, in fact, breaks up as 1 plus I times 1 minus I. Okay. And now what are units? In Z, you only have two units, namely +1 and -1. These are the only ones which, when I multiply it with other integers, I get 1. So 1 times 1 is 1, -1 times -1 is 1. No other number can be multiplied with another integer to get 1. You need a fraction. Now, you can define units even in this larger number ring, and there the units are plus minus 1 and plus minus I. Sorry, that should be plus minus I. Now, we'll come back to this answer, this theorem of Fermat, which was in the 17th century. For all prime numbers P, remember I asked what are the prime numbers which can be written as a sum of two square numbers. So every prime number different than 2, we have that P can be written as a sum of two squares if and only if P leaves a remainder of 1 when we divide it by 4. So for instance, you take 5. When I divide 5 by 4, you have the remainder 1. So 5 can be written as 1 plus 4, which is a sum of two squares. 17 leaves a remainder of 1 when I divide by 4. That is again 16 plus 1, right? So, or you can also write it as 16 plus 1. So, and that leaves a remainder of 1 when I divide by 4. And this is an if and only if condition. Any prime number can be written as a sum of two squares if and only if it leaves a remainder of 1 when I divide by 4. So this way is easy. So if I can write a prime as a sum of two squares, then it's easy to show that it leaves a remainder of 1. This requires only basic arithmetic. But the other way, to go the other way, that is, if I take a prime number which has the property that it leaves a remainder of 1 modulo 4. So for instance, 29. To know that 29 can be written as a sum of two, 29 is still a small number. You can do it by hand. But as the numbers grow larger, to know that if it leaves a remainder of 1 mod 4, then it can be expressed as a sum of two squares. That requires very deep algebraic number theory, which again was discovered by mathematicians 200 years ago, purely out of interest in understanding numbers. And today this has applications in other areas of cryptography and data transmission and so on. So this again, I hope underlines the beauty of mathematics and the challenge of abstract mathematics. And let me stop here and I'll take questions. Thank you.
Thank you very much, ma'am. Now, this is the time to take questions. Ma'am, shall I read the questions from chat box?
Yeah,
for
no,
you?
I'm reading it myself. Is there
Okay,
a
ma'am.
certain difference between prime and co-prime number? There's nothing called a co-prime number. You only say that two numbers are co-prime if they do not have a common divisor. So take any two numbers. If they don't have a common factor, then you say that those two numbers are co-prime. But prime is for a single number. Given a number, you say that number is prime if it is a prime number. Now, a real life example of prime number, I gave you lots of real life examples of prime numbers. Application of prime numbers in real life situations, I told you that it's used in cryptography. The bigger your prime number, the more secure your crypto system is. Your internet banking today or all your Paytm and everything would be impossible without prime numbers.
Dignitaries in the panelists can also please ask queries if they have.
Madam, I have one question.
Yeah.
How much Vedic mathematics is helpful in study of prime numbers?
You know, there's nothing called Vedic mathematics. I mean, what is there in the Vedas are amazing. There are large numbers, very precise large numbers.
Okay.
But Vedic mathematics is a misnomer. So you can Google, I'll tell you the name to Google. You just Google this chat. I'll give you a chat here. Dani Vedic mathematics. So Professor Dani was a professor at Tata Institute of Fundamental Research. And he's written an article on why it's called Vedic mathematics. and it has nothing to do with the Vedas. Now, the Vedic mathematics, I'm not an expert on Vedic mathematics. I know that it consists of a series of steps in order to, let's say, perform multiplication faster. And we have tried it in a few places, and it's not clear if the children can remember the steps to perform.
Okay. Thank you, madam.
Any other queries
One
from
more question is
panelists?
there in the chat.
I think I answered all the questions.
Ma'am, there is another question from Dr.
Okay. What's the involvement of group theory in the theory of primes? Okay, there are lots of questions. Well, you can use group theory in the study of primes. So there's something called additive number theory in which group theory shows up. But apart from that, group theory has certain applications in the study of primes. So for instance, I mentioned this gaps between primes, right? As we go further and further, what can you say about the gaps? So Tao, I mentioned Tao's article. By the way, Tao runs a very nice blog. He writes continuously, and you can read his blogs. They are kept simple and they are written for a lay audience. And I mentioned that he uses some techniques called from an area called harmonic analysis. There's some group theory which comes up in harmonic analysis. So group theory shows up when you want to do finer and finer analysis of primes. But that's roughly a broad answer without getting technical.
No, ma'am. Ma'am, I have a question that what is Iwasawa theory?
Okay, that's very complicated to answer. See,
Okay.
I'll try to answer it in simple terms.
Yes.
I hope many of you know an equation for a straight line, right? It's of the form ax plus by equals c. If you take the plane and you want to draw a line and then you want to find all the points which lie on the line, they all have to satisfy a certain equation, ax plus by equals c. So similarly, the equation for a circle is of the form, let's say a circle with the center origin. Let's call 0, 0 in the plane. That is a center, and you want to understand all the points on a circle with 0 as the center of the circle. Then the equation for something like that will be x squared plus y squared equals r squared, where r is the radius of that circle. So if I take a circle with unit radius, then it will look like x squared plus y squared equals 1. Now we know that this on a circle, there are infinitely many points. So it has infinitely many solutions, right? So more generally, if I take x squared plus y squared equals z squared, then you know that there are infinitely many numbers which satisfy this equation. Anything, if you take the sides of a right angle triangle, so for instance, 3, 4, 5, 12, 5, 13, these are all numbers which satisfy x squared plus y squared equals z squared. But now the minute you go from 2 to greater than 2, so you look for solutions of the form x, y, z satisfying x cubed plus y cubed equals z cubed, or x to the power 4 plus y to the power 4 equals z to the power 4, and so on. Then there are only finitely many solutions. And the solutions all have to be of the form x, y, z equals 0. That is, one of them has to be 0, either x or y or z. And this was a conjecture. Fermat wrote it down. And he said, I know a remarkable proof of this. Remember, I mentioned Fermat in the talk. This was sometime in the 17th century. He said, I know a remarkable proof for this statement, but unfortunately, the page margin is too small for me to write it down. And then people spent 350 years, developed a huge amount of theoretical mathematics along the way to find out what Fermat's proof could have been. Then finally, today, the conclusion is that Fermat must have made a mistake in his proof. And we even can guess what mistake he made. And it is related to the mistake that in Z, every prime is an irreducible. I mentioned that. Whereas in Zi, I showed you that 2 is not irreducible anymore. Right? He made a mistake that primes and irreducibles are same even in these bigger objects like Zi and so on. So once you make that mistake, then you can prove his conjecture. But it took 350 years. Today it's a theorem. It was proved at the end of the last century. by Wiles, and it's one of the most important theorems proved in number theory. But along the way, a whole lot of abstract mathematics was needed in order to prove that. And one such tool is Iwasawa theory. It's a little complicated. I cannot get technical after this. So I just tell you a use of Iwasawa theory.
Ma'am, one personal question I have. Mostly females have to make sometimes compromise with their career due to family responsibility or social boundness. Ma'am, have you encountered such situation in your life and how you come up with the situation? This will be a great message for our young students, especially
Well,
for females.
yes and no. I would say more no, less yes. Yes, in the sense of not having enough support at the workplace. And also having to adjust in the family. Fortunately, I had a very supportive husband. And, my grandmother would always come and help me when I had to work for an exam or when I was busy and so on. So I had family support. But at the workplace, it would have been so much more helpful if there was workplace accommodation, if there was daycare at the workplace. All those things were missing in the 80s and 90s when I was a PhD student. I was very lucky to have a great mentor. I don't know if you've all heard of course, my advisor was a woman, Parimala Raman, who's a great mathematician herself. So she understood what it was to have to do math, and she was very supportive. But more than her as a role model was also her advisor, Professor Sridharan, who was remarkable in the role of a mentor and also a supporter. Not patronizing, but empowering. And we need more people like that. There's a difference between patronizing or, giving out the message that, look, I'm supporting you, even though I know that you're not good enough, I'm supporting you. To empowering, which is making you believe that you can do far better and you're capable of it, and creating the conditions for you to be better. And Sridharan was like that. So we need more people like that, and more institutional support go a long way.
Thank you very much, ma'am. Thank you, ma'am, for taking us to the journey of the wonderful world of prime numbers and sharing the importance of prime numbers in the field of cryptography. Your enlightening address will certainly have a lasting impact on our young students and audience and pave their way to the forefront of the innovation. Now, as gradually we have reached to the end of the program, I request Dean Faculty of Sciences, Dr. K. N. Guru Prasad, to propose the words of thanks. Over to you, sir.
So just a minute, there's one more question. Do odd perfect numbers exist or even perfect numbers infinite? These are open questions. It's still an open question.
Okay, ma'am.
See, these are the kind of questions which are basic, but for whose answers we still don't know. And they are deep questions. You need much more techniques in abstract.
Yeah, ma'am, few more questions have come after your last responding to it. Yeah.
Right. So I think now I've answered everything. Yeah.
Okay, ma'am.
Okay, Pragya, can I?
Ma'am, should we proceed?
Yeah, please.
Yes, please, sir.
Okay, thank you. I'm here to propose a formal vote of thanks to our distinguished speaker, Dr. Sujata Ramdarai, whose lecture was well understood by all those who had a mathematical background. But for a person like me with biological background, I could only understand a bit of it. But 2 points I would like to make before I thank Dr. Sujata Ramdarai. One is, as a layman, I could understand how the gap between abstract mathematics and its applications in the computer era have been bridge now with maybe few centuries, or I don't know, maybe it is 1,000 years or more. That is what I I could see in her lecture, and that's very amazing. That because I work in the area of biological sciences, but uh, in all other areas of science, uh, the findings of 1,000 year back, it is bound to tumble sometime or the other, and it does not survive so many years like
Yeah.
mathematics has survived.
Yeah.
I do not know whether Dr. Sujata madam agrees with this.
No, I agree. But in fact, if I may, I would like to interject here.
Yeah, please.
Mathematics is always ahead. So, for instance, abstract mathematics, which mathematicians did in terms of what's called knot theory and so on, today is finding applications in understanding protein folding and unfolding.
Absolutely, absolutely. The whole bioinformatics is dependent on the
Exactly.
advances
So,
in computer
mathematics,
science.
abstract mathematics is always ahead of its time.
Yeah. That came out very well in your lecture. That how much ahead of it is. It is ahead by thousands of years, which we did not know. Um, that's one point I wanted to make, and another point is today is Dr. C.V. Raman's Day of Discovery, on which the Science Day is celebrated. One of his observations, which also came in the documentary, was that scientific research requires independent thinking and hard work and not equipment. Now, this has changed over the years now after C.V. Raman, because except in mathematics, now mathematics, I guess, also requires computers.
Yes, it does.
So, and other areas, particularly in biological sciences, our advanced research is so much dependent now on the equipment that we cannot do what C.V. Raman could do, say, years back, or what others could do at those times. So that's one change that has happened. Although uh, a large contribution comes from independent thinking and hard work, that's a separate thing. But now, along with that, maybe we also require advanced equipment to do research. So I just wanted to.
No, that's
Yes,
very
yes,
true.
Dr. Sujata.
No, that's true. And again, it's interesting. For instance, you need, let's say in biology, MRI imaging has led to such amazing
Absolutely.
advances.
Absolutely.
But again, there's a lot of mathematics which was done 100 years back, which is used in interpreting images.
Yeah.
MRI, NMRI and MRI has mathematics. Mathematics plays a key role in image recognition.
Even now, I feel that still mathematics can be done without an equipment, but not other areas
Correct.
of science.
Exactly,
So,
I agree. But and it's true that even when we use equipment, we don't need billions of dollars worth of equipment.
that's true, at least for mathematics. So, with this, I wish to thank once again Dr. Sujata Ramdarai. She came to Indore long back as a Bhatnagar awardee. We had invited her to DAVV, and I happened to be there in DAVV at that time. So I remember, and we extend our invitation again to Dr. Sujata Ramdarai to visit our institute sometime. Whenever she finds time, that it will be interesting for all the mathematicians to interact with you and our students to interact with you.
Sure,
So,
we'll be happy to.
yeah. So we keep this in mind and we extend our invitation to you whenever it is suitable to both of us.
Sure.
So thank you very much, and I thank the members of Science Club, particularly Dr. Pragya and also Dr. Neetu Kataria for organizing this Science Day celebrations and inviting one of the best mathematicians we have in our country. Thank you very much.
Thank you and goodbye.
Thank you very much, sir. Thank you very much, ma'am. Now, as we reach the end of the oration, I request every one of you to kindly rise for the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल गंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you very much, ma'am. And once again, thank you very much to all the dignitaries and audience for joining this 6th Sir C.V. Raman Memorial Oration. Good day to all of you.
Thank you.